Hi, I'm Arnie Gundersen from Fairewinds, and this is the first video on the new Fairewinds site. We worked really hard to make it user-friendly and searchable, and we hope you like it. If you have any questions, please send us a comment. You'll recall Marco Kaltofen. He presented at the American Public Health Association a couple months ago, and we aired his presentation. Well, today I had a longer conversation with Mr. Kaltofen. Mr. Kaltofen runs the Boston Chemical Data Corporation, and he's a professional engineer. And he talks about radiation in the environment, and especially radiation from the Fukushima accident. I hope you enjoy the conversation between Mr. Kaltofen and me. Yeah, the one on the right is the fascinating one. Well, and these are the isotopes that I picked up in the soil.
Oh yeah, exactly
in Tokyo. I mean, so the isotopes you're finding in indoor air filters are exactly what I'm picking up in the soil.
That's why those soil samples you sent are completely non-controversial, because what's in them is exactly the same as what's in every other sample we've gotten from the same area.
Yeah.
For the 100+ samples, every one of them has cesium-134 and 137.
Right.
Some low, some not so low.
Well, we had cobalt too, and this has got cobalt and
cobalt-60. Another common thing that we see. When we did the air filters from the car engines, a few things that were interesting about it. A lot of these are from commercial or fleet vehicles, so we actually have a log about where they were driven, when they were used. The car filters, the way people drive in Japan, the number of miles that people do, the size of these vehicles. Stoichiometrically, a car engine filter processes about as much air in a day as a hardworking adult would process. So 10 to 30 cubic meters of air a day for a filter or for a person. So it's a nice qualitative model. So what you're seeing in some of these filters is what you would expect to see for a person exposed to the same air. So the idea of using the car filters was to take a large number of car filters and try and get a feel for whether or not we were getting radioactively hot particles outside the evacuation zone. And this is one of about 4 different methods we've used for looking at air and dust in Japan and the US and Canada. And this method was meant to give us that kind of like bird's eye view about what's happening. And what you immediately see when you look at this is Fukushima City, Tokyo, Seattle. I like this graphic because it's a fast, easy way to show, look, Fukushima City, even though you're 65 kilometers away, we pick up an enormous number of hot particles in these engineer filters. In Tokyo, we're still getting those hot particles. We're not at the levels where people are evacuating, but we're at the levels where people need to think about how they're going to reduce dust exposure overall. That's just a good public health practice. And then in Seattle, I call this my stop whining graphic, because really, there's not much happening in Seattle. West coast of the United States, lower the stress level. We're fortunately not seeing it there. If anybody is going to see radioactive transport outside of Japan, I would think at this point we're going to see it in the marine environment, not in the air. We're going to see a lot more of it coming through the ocean, maybe through food coming from the ocean, then we're going to see it in these airborne plumes. And this sample for Seattle was collected during the time of maximum exposure, which was mid-April. That's when we had the highest rise, almost a doubling of background levels that lasted for about 2 weeks in the middle of April. The human lung is very good at picking up certain size dust particles. The range of dust particles that the lung is good at retaining is from about 0.5 to 5 microns. And if you're not familiar with that unit, it's really a millionth of a meter or a thousandth of a millimeter. These are microscopic sizes. Things that are bigger never make it down into the deep lung. Things that are smaller tend to come in and then they get exhaled out again without sticking. So the particles that are in that size range are the important ones. And that's what my research project is about. How many of the dust particles are in the size range that's actually important for human lung exposure? If they're too big or too small, they're less of a problem for human health. But I need to know not the type of radiation so much, but I need to know how big the dust particles are that carry it and what they're made out of. When you know how big the dust particle is and what it's made out of, you can learn a lot about where it's going to end up in the environment and how people will be exposed. So all that stuff about, you're exposed to radiation in an airplane from cosmic rays or from eating bananas or whatever, it's just nonsense when you're thinking about trying to measure radiation exposure that's important for human health. That's a completely different ballgame. And that's what the dust research is all about. Right? So what we'll do is, we have our filter that's placed up on this X-ray plate. So because we can see the dark spotting from the radioactive particle, we can actually cut this piece out of the filter, and it goes on a little piece of, well, it's essentially expensive double-stick tape. And it's this high-carbon double-stick tape that we use that goes straight into the scanning electron microscope. And then you can actually look at the microscopic particle. You can take its picture. And we hit it with an X-ray beam, and that will tell us the composition of that particle. So if there's uranium in it, or if there's americium or cesium, we'll see that. Now, can't tell the difference between radioactive cesium and non-radioactive cesium, but there is no non-radioactive form of americium, for example. For those compounds, we can be certain. Kids were tracking in radioactive material on their shoes from being in contact with the outdoor soil. And this is also being done with gamma spectrometry. The nice thing about children's shoes is children obviously get outdoors and they play in the dirt more than adults. Children's shoes are small and they fit in my detector better. So we get better results working with kids' shoes. Gives us an idea of what we're looking at. We have never detected radioactive material from Fukushima in children's shoes in the United States. None of the samples are positive. All of our shoes from Japan show that there's cesium-134 and cesium-137 present.
So this is total, both of them.
That's the two combined,
Yeah.
that's right.
When I was in that park in Tokyo, when I took the sample by the tree, that was decontaminated, and still we had high cesium and both cesiums. And kids were running by throwing stones at each other, just like kids always do.
Yeah.
So I'm thinking, they grabbed the stone on the ground, they threw it, and here I am measuring the ground, and so if it's on their shoes, it's on their hands. Let's say it.
It's on the shoes. Well, it was on the shoelaces, for instance. We found that the radiation was also on the shoelaces. And when we do this X-ray autoradiograph, where we actually take the shoe and we put it on a piece of X-ray film, you can see the spotting from the radioactive particles stuck to the soles of the shoes. One of the things you get from looking at the individual particles, the individual hot radioactive particles, you can tell the difference between radioactivity that comes from a natural source or from an industrial source. You can tell the difference between a particle that comes from Chernobyl or one that comes from Fukushima. They look different, they have different chemical compositions. In the example of Fukushima and Chernobyl particles have cesium-137. Fukushima particles have cesium-137 and cesium-134. So it's a signature, it's a fingerprint for the radiation coming out of Fukushima. So if you find a particle that has about the same amount of cesium-134 and 137, and it's less than, say, 20 microns or so, and you found it on the west coast of the United States, that's telling you that you found a particle of radioactivity from Fukushima.
But if there's no 134, it's from bomb testing or from Chernobyl.
Could be bomb testing, could be Chernobyl, could be old radioactive waste, could be from a research reactor, but it wouldn't be from Fukushima. So one of the things that we will be able to do is tell you whether the radioactivity we're detecting is natural or not. But we get that all the time with folks who use the Geiger counter to test something in their backyard or something that rained out. Now that people are a little bit more aware of radiation in the environment. And the nice thing is to be able to say, well, while it's radioactive, it has nothing to do with Fukushima.
I have a question. Last night we were at a panel discussion in Massachusetts, and one of the panelists, who's a nuclear engineer for the industry, said that it's all radiation. Radiation is natural, it's background, there's nothing to be worried about, we don't have to worry about any radiation, things that are coming off of Pilgrim as a nuclear plant don't matter, because radiation is ubiquitous and it's part of our natural background. Can you differentiate that for the viewers?
Sure. I mean, I think that's an interesting attitude because we'll go back to the radon issue. We've got the U.S. Environmental Protection Agency has made a major push to try and get people to test for and, where necessary, reduce their exposure to radon because it's a significant health hazard. It is part of the radiation background. Background is not the same thing as safe. It's a public health problem that has been accepted. There is a government protocol for doing your testing, and there's some simple remedial steps that you can take, and they don't break the bank. So I don't know why one agency of the government would say, you know, the agency that's most concerned with environmental health, why are they saying this is a serious health problem that we need to work on? And someone else says, well, it's background, it's okay. Background is not okay. I mean, we all have natural ailments, things that harm our bodies. I don't care if they're natural. We'd rather stay healthy. So I'm a little confused about that one.
The one that gets me, and it came up in the meeting last night, was the radioactive banana. And you know, we all have potassium, and our bodies